Hello and welcome back to another weekly lesson in Math 1106, Business Precalculus. My name is John Adamski. This week we're going to be talking about factoring algebraic expressions. This is really a technique you're going to need to know very well when it comes to calculus. It's a technique that's used generally to solve equations, though we won't be solving any equations today. We're just going to focus on this first step of factoring algebraic expressions. We're going to look at four techniques for how to do this. The first being pulling out a greatest common factor among several terms. The second being able to identify when the expression we're looking at actually is a perfect square or a difference of squares and how to factor those. We're going to look at a technique called factor by grouping, which will apply when there are four terms that need to be factored. And lastly, we'll dive deep into how to factor quadratics, which are second-degree polynomials that look like this. Okay, let's get to it. All right, so let's talk about greatest common factor and what we mean by that. The greatest common factor of two or more positive integers is the largest integer that they are both multiples of. There's probably a better way to say that grammatically, but the better way to say that is to say that it's the greatest common factor, okay? It is the largest or greatest integer that they are both multiples of. Both multiples of. Those are common factors, okay? As an example, let's talk about the greatest common factor of these two numbers, 60 and 126. Now, just to be careful with the language here, the factors of 60 are all the numbers that 60 is a multiple of. There's a lot of them, actually. But they come in pairs. So, 60 is 1 times 60. It's also 2 times 30. It's 3 times 20, 4 times 15, 5 times 12, 6 times 10. They come in pairs, and those are the factors of 60. The factors of 126 are written below. Okay, now what numbers appear in both? 1 appears in both. 1 is a common factor. 2 is a common factor. 3 is a common factor. What's the largest common factor, aka greatest common factor? Well, I think it's 6. I think 6 is the largest number that appears in both of these rows. Okay, so 6 is my greatest common factor. Now, that's not a very sophisticated way of doing this. This is a very brute force way of doing it, listing all of the factors. And it won't really translate well into algebraic expressions. But there's another way to look at this. It has to do with prime numbers. You might know that a prime number is a number whose only factors are 1 and itself. Now, 60 and 126 are obviously not prime. They have many factors. So one way to factor 60 or to write it as a product is to write it as 2 times 30. Now, 2 is prime. It can only be factored into 1 and 2. But 30 is not prime. It can be factored into, for example, 2 and 15. 2 is prime, but 15 isn't, so I'll keep going. 15 can be written as 3 times 5, and both 3 and 5 are prime numbers. So this procedure stops now. And what this shows me is that 60 is equal to 2 times 2 times 3 times 5, or in other words, 2 squared times 3 times 5. Now over here, let's do the same thing for 126. 126 is not prime. I can factor it into, for example, 2 and 63. 2 is prime, but 63 isn't. I can factor 63 into 9 times 7, for example. And 7 is prime, but 9 isn't. 9 is 3 times 3, but 3 is prime. So this now stops, okay? This is called a factor tree, and this shows me that 126 is equal to 2 times 3 squared times 7. Okay, so what we're looking at here is the prime factorization of those numbers. And if this was a number theory course, we might dwell on that for a little bit longer. But all I want to do is show you how once I've broken them down into powers of primes, it's very easy for me to tell you what the greatest common factor is. It's simply the product of common factors raised to the lowest exponent. So what are my common factors? Well, there's a 2 here, and there's a 2 here. So 2 is a common factor. These are both multiples of 2. And 3 is a common factor. There's a 3 here and a 3 here. Those are both multiples of 3. 60 is a multiple of 5, but 126 isn't. This is a multiple of 7. This one isn't. So this is the end of my list of common factors, just 2 and 3. And what I do with that is I say the GCF is the product of the common factors, 2 times 3, raised to the lowest exponent. Now this 2 has an exponent of 2, but this 2 only has an exponent of 1. So the lowest exponent would be 1. Of the common factors of 3, there's an exponent of 1 here, of 2 here. The lowest exponent is, again, 1. The GCF is the product. 2 times 3 equals 6. Let's take this to the next level and look for the greatest common factor of 2 algebraic expressions. Now, to begin with, we have coefficients of 8 and 14. Now, the greatest common factor of 8 and 14 is 2. These are both multiples of 2, and that's the largest number that these are both multiples of. Moving on to the more complicated part when it comes to the variables, I'm going to follow the same rule that we followed before. I'm going to make the product of the common factors raised to the lowest exponent. So out of x, y, z, w, x, y, which are the common factors? The common factors are x and y. There's an x here and an x here. There's a y here and there's a y here. Z is not a common factor because there are no z's over here. And w is not a common factor because there are no w's over here. Now, what powers are these raised to? We should raise them to the lowest exponent. When it comes to x, the exponents are 3 and 6, the lowest one being 3. For y, the exponents are 8 and 4, the lowest one being 4. That is the greatest common factor. Okay? And that's an isolated exercise. That's the answer. This is the greatest common factor. What that means is that both this expression and this expression are multiples of this expression. In part B, I'm asked to factor the first term plus the second term. It's the same terms. Okay? Now, the verb factor means to write something as a product. So I want to rewrite this sum as a product. I want it to be something times something else. And the trick here is to make use of this greatest common factor. Both of these things are actually multiples of this. So I'll write it this way. I'll write down the greatest common factor, 2x cubed y to the 4th. So we've already handled that. That's the greatest common factor. And I know that both of these expressions, I should be pointing here, both of these expressions are multiples of this. Now, what would you have to multiply 2x cubed y to the 4th by to get 8x cubed y to the 8th z to the 5th? Well, the 2 would have to be multiplied by a 4 to get 8. X cubed needs to get multiplied by 1 to get x cubed. It already is x cubed. Y to the 4th would need to get multiplied by y to the 4th to get y to the 8th. And there are no z's here. To get a z to the 5th, I would also need to multiply this by z to the 5th. Now, you can check that this times this does give me this first expression. What would I have to multiply this by to get positive 14w squared x to the 6th y to the 4th? Well, the 2 would have to get multiplied by a 7. The x cubed would have to get multiplied by x to the 4th. Or, I'm sorry, x cubed would have to get multiplied by x cubed. X cubed times x cubed is x to the 6th. Y to the 4th, I already have the right number of y's. Oh, I skipped over w. There are no w's here. I need to multiply this by a w squared. Okay? So if you perform the distribution, you will recover the previous line. What we've accomplished is that now we've rewritten this expression as a product. It is something times something. It has now been factored. Okay? Let's look at this example over here. I want to do the same sort of thing. I want to factor this difference. This is not a product. This is a difference. It's something minus something, but I want to write it as a product. Well, I'm going to look for that common factor, that greatest common factor. And when it comes to the coefficients of 4 and 6, those are both multiples of 2. So I can pull out a 2. Then I'm just going to proceed to write down the product of the common factors raised to the lowest exponents that I see. So I see an x here and an x here. So x is a common factor. And out of the exponents that appear, 3 and 2, the lowest exponent is 2. There's an x minus 1 over here. There's an x minus 1 over there. That's a common factor, x minus 1. The exponents that I see are 2 and 3. The lowest one is 2. Okay? There's an x minus 2 here, but there's no x minus 2 over there, so that's not a common factor. This is now the greatest common factor. And what we're left to do is write down what would you have to multiply this by to recover the original expression, to recover this minus that. Well, what would this need to get multiplied by to bring back this first term? We have a 2, we need a 4. 2 times 2 gives us 4. We have x squared, we need x cubed. X squared times x gives us x cubed. We have x minus 1 squared, we need x minus 1 squared, so we're good. We don't have any x minus 2's over here, but we need 1, so we need to multiply this by x minus 2. Okay? What would you have to multiply this by to recover the second expression? Well, we need a minus 6, and we currently have a positive 2, so we need a minus 3. We have x squared, we need x squared. Good there. We have x minus 1 squared, we need x minus 1 cubed. We need an extra x minus 1. And that would recover the last term. So this has now been factored. We can clean this up a little bit. Let's write this as 2x squared times x minus 1 squared. And inside this bracket, I'm just going to perform the distribution. So I'm going to get a 2x squared, also a minus 4x, and a minus 3x gives me a minus 7x. And lastly, minus 3 times minus 1 gives me a plus 3. Okay, so this would be my final answer in factored form. And in my last example here, I want to factor this expression. Now I've got some square roots and some denominators, but of course all of this can be handled with exponents. So I think the first thing I'm going to do is just rewrite this using exponential notation. So this square root of 2x minus 3 is really a 2x minus 3 to the 1/2 power. And this x cubed in the denominator is really an x to the negative 3. This is just another way of writing it. Plus, what do I have here? Well, that 2 in the bottom, I'm going to write that as a coefficient of 1/2. Okay? And then you've got an x, and then you've got a square root of something in the denominator. That means that that 2x minus 3 to the 1/2 power in the denominator is a 2x minus 3 to the negative 1/2 power. Remember negative exponents from last time. Okay, so I want to factor these things. And so I'm going to do what I said I was going to do. I'm going to write down the product of the common factors raised to the lowest exponent. I'm going to pull out the greatest common factor. So I see x here and x here, so x is a common factor. And out of the exponents of negative 3 and 1, the lowest exponent is negative 3. I see a 2x minus 3 here and a 2x minus 3 there. That makes it a common factor. And the exponents that I see are 1/2 and negative 1/2, the smallest one being negative 1/2. Okay? That's the greatest common factor. Now, what would I need to multiply this greatest common factor by to recover the original terms? I know that this is a multiple of that, so show me. It's this times what? Well, x to the negative 3, x to the negative 3, we're good there. 2x minus 3 to the negative 1/2 times what would give us 2x minus 3 to the 1/2 power? Well, the answer is 2x minus 3 to the first power. Why? Well, this base and this base are the same, and when I add those exponents, which is the rule for exponents, 2x minus 3 to the negative 1/2 times 2x minus 3 to the positive 1, when I add negative 1/2 plus 1, I get positive 1/2. Negative 1/2 plus 1 is positive 1/2. So this multiplication recovers the original term here. To recover the second term, I need a 1/2. We're going to need to multiply this GCF by a positive 1/2. We have x to the negative 3. We need an x to the positive 1. That means we need an x to the 4th. X to the negative 3 times x to the 4th. We add those exponents together. That will give me the 1 that I need. And I have a 2x minus 3 to the negative 1/2. I already have that here, so I'm done. Okay? And in this particular case, raising this to the first power is that you don't really need to write that. And these parentheses aren't really doing anything, and there's no similar terms to combine here, so this is my final answer. All right, so after pulling out greatest common factors, Another technique for factoring is to take advantage of the special product formulas that we saw in the last lesson about distribution, where we took something like a plus b times a minus b, performed the distribution, and showed that this is equal to a squared minus b squared. Well, then it stands to reason that a squared minus b squared can be written as the product of a plus b times a minus b. That is to say that this difference of squares factors in this way. Okay? And let's just pause there for a second and work on this example, because this is a difference of squares. If you're not seeing it, this is 3x squared squared minus 8 squared. It's a difference of squares, and so it's going to follow that formula. You have something squared minus something else squared. It's going to equal the first thing plus the second times the first thing minus the second. And we see exactly what those things are. A is 3x squared. So we have 3x squared plus b, so plus 8, times a, that's another 3x squared, minus b, minus 8. And this is the factored expression. Okay, that one's not so bad. That one was easy to pick out because you had a difference of perfect squares. What about this one? Well, it's also a difference of perfect squares, and maybe it's a little bit more obvious because we're just seeing exactly, this is a perfect square minus a perfect square. So it's going to follow that same pattern of a squared minus b squared equals a plus b times a minus b. Okay? So let's just see, what is this equal to? Well, a plus b times a minus b. A is 4x minus 5, so we've got 4x minus 5, plus b, so plus 6x plus 1, times a minus b. A again is 4x minus 5, minus 6x plus 1. Okay? In this case, I can, inside each bracket, I can combine similar terms. So let me do that. Let me write this as 4x plus 6x gives me 10x. Negative 5 plus 1 gives me, minus 4. Okay? And inside this bracket, what do I have? I have a 4x minus 6x. That's a negative 2x. And a negative 5 minus 1 gives me a negative 6. Okay, I could stop here. I have factored it. I have written this difference as a product, but I can go a little bit further. The idea of pulling out the greatest common factor really should always be considered and never goes away. So just between 10x and 4, there is a common factor of 2. I could pull out a 2, and it would leave behind a 5x minus 2. Distributing that 2 recovers the original expression. And similarly over here, I could pull out a 2 or a negative 2. It really doesn't matter. Let's try pulling out a negative 2, and then I'd be left with x plus 3. Distributing that negative 2 recovers the original expression. So another way to write this would be to say, well, 2 times negative 2 is negative 4. And then I have a 5x minus 2 and an x plus 3. And now it's been factored. Now, the other special product formulas that we learned in our lesson about distribution are these ones, where you take a sum and square a sum. A plus b squared gives you a squared plus 2ab plus b squared. And the difference of two terms squared, this is also called a perfect square, is a squared minus 2ab plus b squared. Okay? When you have a plus sign here, you have a plus sign here, a minus sign here, a minus sign here. Otherwise, these formulas are identical. All right, this is a little bit trickier to see, but I'm going to walk you through this and hopefully you'll pick up on what's going on. So I'm asked to factor this expression, and this could be kind of tricky, but the key observation is that this right here is a perfect square, and this right here is also a perfect square. This is a sum of 3 terms that begins and ends with perfect squares, just like this expression right here begins and ends with a perfect square. So let's start to make that clear with the way that we write this. Let's write this as 6x squared. Okay, that's what 36x squared is. And this last term is 5 squared. Okay, so we've got something squared plus something else squared. And that middle term, let's see. We know right here, I'm just going to copy this down, that a squared plus 2ab plus b squared can be factored. And is that what we have? Well, the a is 6x, so this would be 2 times 6x times 5, b is 5, and it just so happens that, 2 times 6x, which is 12x, times 5 would give you 60x. So this is the original expression. It happens to be a squared plus 2ab plus b squared, where a is 6x and b is 5. So knowing that this factors into a sum of a plus b squared, in other words, this is a perfect square, this factors into 6x plus 5 squared. Okay? Now what about this one? Again, this might seem like hard to think of, but my attention is on this first and last term, and I notice, that's a perfect square. That happens to be 2x cubed squared. And this last term at the end, the plus 49, happens to be a 7 squared. So now I wonder, well, that's a squared, and this is b squared. I wonder what that middle term is. Is it equal to 2ab? Because if it is, then I know, or I'm sorry, it's minus. So is it equal to minus 2ab? Because if it is, then it factors into a minus b squared. So let's see. The role of a is being played by 2x cubed. So what would be minus 2 times 2x cubed times b? The role of b is being played by 7. So I'm asking myself at this point, is this the same as what's above? Well, let's see. I know that the first term is 4x to the 6th. I know the last term is 49. What's this? This would be minus 2 times 2 times 8. That would be minus 28x cubed. Minus 28x cubed. So yes, this works. What I was handed, this expression, does match this form of being a squared minus 2ab plus b squared for this particular value of a and this particular value of b. And so I know that it actually is a perfect square and factors into a, or 2x cubed, minus b, or minus 7 squared. And that's my final answer. Here's another technique of factoring algebraic expressions that applies when you are factoring the sum of 4 terms. Okay, so you'll know to use this when you're faced with factoring something that is the sum of 4 terms like I have here. All right, I'll walk you through the procedure using this as an example. So what should I do? Well, the trick is instead of looking for a greatest common factor among all 4 terms, which in this case there is none, I break this up into 2 groups. Okay, so I'm going to look at the first 2 terms and the second 2 terms separately. Now from these first 2 terms, or this first group, is there a greatest common factor? Well, yeah, as far as 6 and 15 go, those are both multiples of 3, so I could pull out a 3. And the x is a common factor, and the lowest exponent that appears between the 3 and the 2 is a 2. So 3x squared. These are both multiples of 3x squared. Pulling that out, it leaves behind a 2x minus 5. 3x squared, if you were to distribute it to these 2 terms, you would recover these original 2 terms here. Now from the second group, 4x minus 10, from the 4 and the 10, those are both multiples of 2, so I could pull out a positive 2. There's an x here, but there's no x here, so that is the common factor. It's just 2, and it leaves behind a 2x minus 5. If you distribute that 2, you get 4x minus 10. Okay, so everything is right here. So I split it into 2 groups, and I factored out the GCF from each group. The last thing to do is to factor out the common factor. Now, this doesn't always work, but it's worth trying whenever you have 4 terms, and in this case it does work. There is a common factor that's revealed itself. There's a 2x minus 5 here and here. So let's pull that out. Let's factor out a 2x minus 5. That's the common factor. And what would you have to multiply 2x minus 5 by to recover this original expression here? Well, 3x squared, of course. And what would you have to multiply it by to recover this expression here, a positive 2? So this is the factored form of this algebraic expression. Okay? And you can check all of this by distributing this out and making all four products, or foiling this out and seeing that this is the result. Okay? Let's look at another example. It's quite similar. Again, I have 4 terms. I'm just going to dive right into factor by grouping to see if it works. It often does. So I break this up into 2 groups of 2 terms. Okay, that's step 1. From the first 2 terms, is there a common factor? Well, yeah, 32 and 4 are both multiples of 4, so I'll write that down. There's an x cubed and an x squared, so x is a common factor, and in fact, x squared is the greatest common factor. When you pull that out, it leaves behind an 8x plus 1. Okay, 4x squared times 8x gives me 32x cubed. 4x squared times 1 gives me 4x squared. From the second group, there is really no common factor here. So you could just say, minus 8x minus 1. But then there wouldn't be any common factor for me to pull out in step 3. But if you scratch your head for a little bit, you might notice that they're both negative. So you could pull out a negative 1. Okay? You could say, all right, well, I'll pull out minus 1. And then I'm left with just positive 8x, positive 1. Negative 1 times 8x is negative 8x. Negative 1 times 1 is negative 1. This works. And suddenly, there actually is a common factor of 8x plus 1, both here and here. If we pull that common factor out, 8x plus 1, it leaves behind a 4x squared minus 1. Okay, if you distribute 8x plus 1 to these 2 terms, you get back what's written above. Now we can actually go one step further because 4x squared minus 1 is a difference of squares. Okay, so we can write this as 8x plus 1 times 2x plus 1 times 2x minus 1. Okay, I'm just taking advantage of the fact that 4x squared minus 1 is 2x squared minus 1 squared. So it is a difference of squares, and we know that a squared minus b squared factors into a plus b times a minus b, hence 2x plus 1 times 2x minus 1. Now, this is what's called fully factored. It was factored here, but one of the factors could be factored further. Now, none of the factors can be factored anymore. This has been fully factored or completely factored. Lastly, let's talk about how to factor quadratics. A quadratic is a polynomial where the highest exponent is 2. So something like ax squared plus bx plus c is just a generic way to refer to any quadratic. Okay? The only difference between any 2 quadratics are the particular values of the coefficients a, b, and c. How do you write something like this as a product? How do you factor it? Well, there are really 2 cases, and you're probably familiar with the first, which is when the lead coefficient, the coefficient of x squared, what I call a, if a is 1, then it's pretty straightforward, and you probably have a lot of experience doing this. The trick is to find 2 numbers that multiply together to be the last number, the constant term, in this case negative 10, and that add together to be the middle coefficient, the coefficient of x, in this case 3. So it's a little bit of a puzzle, but there aren't that many numbers that multiply together to be 10. 1 and 10 and 2 and 5. But in particular, the product needs to be negative, so one of those numbers has to be positive and one has to be negative. So with a little bit of trial and error, I think you'll find that the answer is 5 and negative 2. 5 times negative 2 is negative 10, and it just so happens that 5 plus negative 2 is 3. So what do I do with those numbers? Well, I write my expression as x plus 5, where I'm using the positive 5, and x minus 2, where I'm using the negative 2. And you can check by foiling this that I do get x squared Here's your minus 2x plus 5x, but we know that minus 2 and 5 add up to 3. So that does give me 3x. And lastly, 5 minus 2. We already know that 5 minus 2 is negative 10. So yeah, that checks. And this is that quadratic in its factored form. It gets a little bit more complicated when the lead coefficient isn't 1. For example, if you were trying to factor something like 8x squared plus 14x plus 3, the fact that that lead coefficient is not 1 makes this a little bit trickier. And there's certainly a way to go about this where you're sort of just guessing and checking, and if you have good number sense, maybe you can figure this out. But here's a procedure that will always work, okay? It's called splitting the middle term. So if you want to learn more about this, beyond what I'm going to show you right now, Google split the middle term, and I think you'll find all that you need. I'm going to split that middle term. By the middle term, I mean the bx term. In this case, I mean the 14x. I'm going to split that into two terms, two x terms, where the coefficients multiply to be the product of a times c, the product of the lead coefficient and the constant, and that add up to b, the coefficient of x in the middle. So it's another puzzle, but the rules have changed slightly. I'm looking for two numbers that multiply together to be 8 times 3. So that's what I mean by a times c. That's 8 times 3, or in other words, 24. Okay? And I want those same two numbers to add up to b, or in other words, 14. So we have to find two numbers that multiply together to be 24 and that add up to 14. There aren't that many numbers that multiply to be 24, and to get them to add up to 14, I think we need 12 and 2. 12 times 2 is 24, and 12 plus 2 is 14. Those are the numbers that satisfy this numerical puzzle. What am I going to do with that? Well, I'm going to take this original expression, and I'm going to rewrite it as 8x squared, and I'm going to split that middle term up into 12x plus 2x, which makes 14x. But in this split form, now we have 4 terms. And what do we do when there are 4 terms? Well, we try factor by grouping. Okay, I group together the first 2 terms, and I look for a common factor. I group together the last 2 terms, and I look for a common factor. Okay, so from these first 2 terms, 8 and 12, there is a common factor of 4. X squared and x, there's a common factor of x, and the lowest exponent is 1. So I can pull out a 4x, and it would leave behind, what, a 2x plus 3. OK, well, over here, I have a 2x plus 3. All right, so what am I left with? Well, there's a common factor of 2x plus 3 here and here. So as factor by grouping goes, I'm going to pull out that common factor of 2x plus 3. Now notice that there is a coefficient of 1 here. That might be helpful to make note of. When I pull out the 2x plus 3, what it leaves behind, you would need to multiply 2x plus 3 times 4x to get this expression. And you would need to multiply 2x plus 3 times 1, positive 1, to recover this last expression. Okay? And this is now that same quadratic, but in its factored form. Let's work through one more example just for good measure. I want to factor this quadratic, 12x squared minus 4x minus 5. And it's a little bit tricky because the lead coefficient isn't 1. In this case, it's 12. So here's my explanation of how splitting the middle term works, but I just have to solve a little bit of a numerical puzzle before I begin. I need to find two numbers that multiply together to be not just negative 5, but 12 times negative 5, which would be negative 60. And I need those same two numbers to add up to the middle term, which is negative 4. OK, so let's see. Scratching my head, let's see, what are the factors of 60, factors of negative 60 that add up to negative 4? Well, let's see, the fact that they multiply together to be a negative number, one of them needs to be positive and one of them needs to be negative. I think what I'm looking for here is 6 and negative 10. 6 times negative 10 is negative 60, and 6 plus negative 10 would be negative 4. Okay? So with that in mind, what do I do with that? Well, I use those two numbers to split the middle term. I'm going to split negative 4x up. This is going to become 12x squared plus 6x minus 10x. That's where I've split that middle term up into 6x minus 10x, which is negative 4x minus 5. And from here, I just use factor by grouping. So from these first two terms, 12x squared plus 6x, there is a common factor of 6x, which I can pull out, and that leaves behind a 2x plus 1. From this second group, negative 10x minus 5, you could pull out a 5. Okay, you could pull out 5, and that would leave behind a negative 2x minus 1. Now, in this case, there is no common factor. There's 2x plus 1, and then there's negative 2x minus 1, and those are not the same. So kind of back to the drawing board, maybe you see that there's a negative here and a negative here. I could pull out a negative sign also. So what if instead of pulling out a positive 5, I pulled out negative 5? Okay? What if I pull out minus 5? Then I'd be left with 2x plus 1, which is great because I have a 2x plus 1 over here. Now there is a common factor, 2x plus 1. Okay? So if I pull out the 2x plus 1, what does it leave behind? 6x minus 5. And now we have factored this quadratic into 2x plus 1 times 6x minus 5, and that's it.